I can't help being me though. Okay, let's jump into Neyman-Pearson. The proof isn't too hard if you understand that master equation. It's basically just thinking about what it all implies. Neyman-Pearson says, and this is the simple versus simple case, this can be extended to the one-sided hypothesis test, but it cannot be extended to the sharp test without additional constraints. So, and we'll talk about that on Monday, what it says. But basically, if the likelihood ratio is not monotone on the sets that you're testing on, which it is on one-sided cases, or the simple versus simple, things go well. And on cases where the likelihood ratio is not monotone, like in the sharp test, where you're testing both sides, so you have this power curve that inflects and it's not monotonic. So the one I drew you for the one-sided case is monotone. So in the non-monotone cases, a lot of the guarantees are off. And I think a lot of people don't understand that. But again, if you just think about the question, testing a point against an interval is kind of a weird thing to do. So we have to say more about what we mean. I will say that Neyman-Pearson, what they're proving everything about is about error rates. So error rate, power functions, that sort of stuff. So it's the errors that they're calibrating. So, and that's the only guarantees that they're really giving us. So these are the people that say things like, well, if P dot's alpha and you pre-specified alpha, that's all you do. You don't think about the size of P or anything like that. It was never meant to be a measure of support, so it's just a decision rule. And that's probably the part that irritated Fisher, is he liked to think about things in terms of a continuum of beliefs. And I sympathize with that. So there's a lot of things that people get approximately right, but we have to figure out where things get all kind of tangled up. So again, it's the sharp test where things get tangled up. Simple versus simple, I think lots of cool things come out of this. So this is the likelihood ratio in disguise, the likelihood ratio test. And what they're basically saying is that if you're going to test things or play around with stuff, sometimes working in ratios or likelihood ratios is a really important thing to do. And so we've been kind of saying that throughout the class. Use likelihoods. If you're going to touch likelihoods and you see them in equations, they should come in ratio forms. And so I think that Neyman-Pearson gives us a little bit more as well, is what they tell us is which test statistic we're supposed to use when we test something. And I don't care who you are. So if you're a Neyman-Pearsonian and you're following this sort of procedure where you form the likelihood ratio test statistic, you figure out what statistic that is that you're bounding by some constant, and then maybe you figure out what the probability distribution of that statistic is so that you can calibrate alpha, the size of the test. I do think maybe all the size of the test stuff and the way they build in the constraint, that could be controversial. There's room for argument there. Ben's already argued about that a little bit. Why do you build the constraint in that way? And I think we all have. You know, why do we treat the null hypothesis so much differently than the alternative? And there might be cases where you don't want to do that. But again, I do think likelihood ratios are the right thing to do, and they give you power to detect differences in things. So the part of this that isn't fully specified is you need to come up with a meaningful distance on the effect size to make this useful. So what I mean by that is you could rephrase this like this, theta naught plus some delta. And that's what theta 1 is. So I want to test if this point is reasonable, and then I want to test it against some distance from there. I think the important part to talk about is this. So the delta, why did you pick it? How far do you have to be from the null hypothesis before you're willing to reject it? And I think this is the part of the conversation that Wald alluded to and said it's the big deal, and kind of people paid a little bit of attention, but it's way easier to teach a class and to grade a class on not what they think is meaningful in the context of some problem that's hard to write down in a testing situation. It's just easier to see if they can state the null hypothesis, get the right test statistic for testing, work out its probability distribution, and conclude. at the end of the day. Pick an alpha level, see if P ducks alpha. I don't think that it should be that algorithmic. I think you should spend a lot of time thinking about what that meaningful effect size is. Let's just go through some math though. So what Neyman and Pearson were probably thinking is that Fisher had concocted this idea of p-values. It seemed reasonable when he said, you know, if the p-value, the more extreme data from what you've observed has a less than 1 in 20 chance of occurring, that's good reason to reject. And he said it just like that in a sentence. And I think that probably most of us would go, sure, let's see what happens. That doesn't sound like a horrible idea. But it can mean different things in different contexts. So the one-sided test, the simple versus simple test, share a lot of properties, but the sharp test doesn't enjoy all those properties. So it turns out you could turn the p-value into a measure that is a meaningful, coherent measure for the one-sided or the simple versus simple case, but not the sharp case. So I'm really trying to lay this on thick, that there is this big difference in the sharp case, and that's where all the contentious stuff is. I'm gonna plan not to test you heavily on that, if I even test you at all. But I want you to be aware of it, so when you hit advanced inference and you hit these other things, you know you're supposed to be focusing on that nuance. And hopefully one of these days, you guys have big protests all around the country on college campus protesting the sharp test. So I would like to see that protest all over the place. I think that would be one that could save lives. So it could, like I'm being a little bit silly about it, but I think it could. And I think it could lead us to more rational decisions and down with, you know, Fisher and Neyman and Pearson, you know, that have sent back the statistics world billions of years because of this sharp test thing. I feel strongly about it. I don't think we should be sharp testing all the time like they teach us in Stat 101. It's almost like they indoctrinated us with it. So there's weird stuff in that test, and again, just the fundamental question, theta naught against the whole real number line, yeah, right, you know? So we need to say a little bit more about that. If you're just calibrating air reads, and that's all you care about, and you're running a conveyor belt, and you're checking something over and over again, I think it's reasonable. Doing a sharp test sort of thing. You can also take the vantage point that they get to a little bit more later in the book on confidence intervals. And so if you learn what a pivot is in advanced inference, I'll leave it there. We kind of talked about it a long time ago when we talked about intervals very briefly. You can come up with a one-to-one correspondence between a p-value. In the sharp sort of test case, you can also do it in the one-sided case. But in the sharp test, you can come up with a collection of values that you would have rejected if you had done the hypothesis test. And there's a nice picture in the book that illustrates that. So there is this correspondence between p-values and confidence intervals in most cases, not in all cases. I'll say more about that next week. And so what I really want to just get to is go through this proof, and then we'll use next week to kind of just jabber on about nuances and things that I probably won't test you on. So let's have one more day of deep thinking, and then we can go into more relaxation mode. I'll tell you about what a Bayesian does on Wednesday, but I won't tell you all about how they do it. I'll just set up the basic structure, see that some of the stuff makes sense, and then I'll tell you where the rub is. Okay, so in this proof, I'm going to say a few things about level alpha, but I'm going to just keep replacing everywhere they say level alpha with size alpha. I'll say a few places in the proof where it's important and what they're getting at. But basically, level alpha means that there's an upper bound on whatever this number is, right here. So I can upper bound that, and I can make the type 1 error rate a little bit higher. So what happens to the power when you make the type 1 error rate higher? The power goes higher. So keep in mind in the alternative region, so I'm talking about the alternative region when I say the power goes higher, the type 2 error rate goes down and the type 1 error rate goes up. So the power in the alternative region is going up. So that's all they're saying with this differentiation between level and size, that I could make the power a little bit higher by making the alpha level higher as well. We'll see that in the proof.
Is that inequality supposed to be the meters So the most powerful is good as one power.
Yeah. This is the statement on UMP is. So that's what UMP is. Oh, sorry, yeah. You don't want it lower, you want it higher. Very good. So we're at least paying attention to our bounds, good thinking at 9 a.m. So yeah, but that makes sense. We want the power to be higher. So UMP tests are basically saying is that uniformly, and what they mean by the uniform thing is it doesn't matter how you pick theta in the first place. So the thetas that you pick, this property will be enjoyed across the whole range of thetas. So that's the uniform part, and the most powerful part just says that the power function is bigger, and so you have the ability to reject the null hypothesis a little bit easier. So if it's not true, and so that's good. So in the alternative region, that's true. So we want to reject in the alternative region, and so when that's what the power function is the probability of rejecting. So again, I think Neyman and Pearson are really cool for trying to go through this argument and trying to explain what maybe Fisher meant by all of this. Unfortunately, they tried to be helpful and it backfired on them. So just a little bit of the history. This is Neyman-Pearson. So there's a little bit of history, and that's what really explains a lot of these debates. Carl Pearson is Egon Pearson's father. And he's a little bit older than Fisher. And just like a lot of good champions, super solid, strong statisticians, academics at the time, if you put two really strong ones in the same room, they won't like each other. So, and sometimes it's like you would ask them a little bit more about what do you mean by all of this, and they would get temperamental. So we all understand that. So sometimes when we have a hard time explaining things, we throw a temper tantrum. And that is exactly what happened between Carl and Fisher. There's this huge temper tantrum where they always fought with each other. Carl took it a step too far. And he basically went around to all of Fisher's potential employers and said, not this guy. I don't like this guy. So get rid of this guy. He doesn't know what he's talking about. He's trying to change and bring in new concepts than the stuff I was talking about. I think Fisher was actually probably right about a lot of those arguments. So with Carl, but I kind of see it as they're all leaning in the same direction and just refining each other, and there's nothing wrong with that. So, but at the time, everybody wants credit for everything, and I think that ego contest is what drove a lot of this. So Carl tries to bury Fisher. Fisher ends up becoming a great champion anyway. So he can't be denied. He's still thinking about stuff. He's working hard. He's putting his family to work to do all his calculations for him. So he's got an army. And then Fisher becomes famous and he starts reinventing this whole everything. Some really cool stuff happened with Fisher. So Box comes on the market, I would say, and he starts coming up with response surface methodology. And guys like Carl are like, no way, you can't do this sequential design stuff, this isn't how we do it, response surface is nonsense. And Fisher says, not so fast. And so eventually Fisher has friends in the Royal Society and says, this is a good idea. So, and Box explodes. And Box is probably one of the best champions because he never really made enemies with people after that. So yeah, a way of saying things. Anyway, Egon, I think, misunderstands what the argument's all about, and he says, I'm going to be buddies with Fisher, and I'm going to try to explain what he means. Inadvertently, he says, really the important thing is not the p-value, it's the alpha level. And that's all that matters, and that's probably what Fisher took issue with, is you're making these sharp decisions. So p-value of 0.049999 and a p-value of 0.05000001 are somehow totally different in their decisions that they lead to. So I can sympathize with Fisher, but at the end of the day, you got to do something. So there is a boundary to everything. And so it didn't work that well, and Egon and Fisher get into probably the most famous debate in all of statistics. And really, I would say where they're arguing the most is the Sharp test. So again, they're arguing about the Sharp test. So there's a theme here. Okay, here's my opinion. Neyman and Pearson are mathematically correct. Fisher is wrong, but Fisher has some good ideas. So really, with this whole p-value thing in general, across all of these different types of tests, we talked about the interval test last night, which is an embarrassment for the, I would say, the p-value is thinking that p is a measure of support. If you want to see more about that next semester. Neyman and Pearson are correct. You can use this to control error rates. If I were doing a science experiment where I just get one data set, cost me $1 million to curate that data set, I'm going to come up with one inference. I'm probably not in a framework where I really want to test error rates because I don't really have the ability to do it. You know, to rerun it and check to see if I'm right or wrong. So it's kind of a hope and a prayer, and I think it's a little bit lost. So like in genetics or something like that, if I want to understand what happened a long time ago in the history of gene flows, I don't get to repeat that experiment. So it'd be really nice if we could create another universe, see what would have happened, and all of that stuff. So I don't think that's a framework where you would see p-values pop up. We don't even know what more extreme means in cases like that. So that's a bit of a problem too, is just defining what more extrema means in multimodal spaces. Okay, so what do people do with all that stuff? They still use likelihood ratios, but they use them a little bit different. Okay, let's do a proof of this. So I think that there's some merit here. I'll leave you with this one last point. Neyman and Pearson never carried out an analysis ever where they computed P, saw that it ducked alpha, and just rejected blindly. So Wall tries to say what they would have done had they done things, and he says they would have drawn the power curve and understood the power curve and defined meaningful differences, i.e. that delta value that I wrote down previously, and study that very carefully. So I think if you are going to use all of this and you're not drawing the full power curve and understanding it and coming up with a delta, a meaningful effect size, how far does the null have to be, how far do you have to be from the null before you're willing to reject it and put that thought into everything, I don't think it's science. So saying that, there's thousands of people all around campus that do exactly that, and they're allowed to have their argument. Okay. I have heard people say, I don't care about all of that, I just want to do science. And it's like, that is your measuring tool for making your decisions. Anyway, think of it as you want. Has to be a little bit of philosophy in this class. Let's go through a proof. So we want to prove this. So last time we had written down the master equation. This is not called the master equation anywhere but in this book. This is just the crux and trying to get you to remember it. So this is what you need to remember. So just remember last time I said delta x is just an indicator function on this likelihood ratio. So it tells us if we're in the rejection region or not. So I'm going to say I've got a delta function pertaining to a test from the Neyman-Pearson Lemma. So the likelihood ratio. So this is going to be a 1 if we're in the rejection region. X is not in the rejection region. And just to be really clear, this means f of x given theta 1 is greater or equal to k f of x given theta naught. So the equality goes the other way. So same thing for x is not in the rejection region. So this pertains to the likelihood ratio test statistic. Just likelihood ratio test and indicator on it. And then we're going to consider some other tests. So if you're a math major, you know what we're setting up. Right here, I'm going to consider some other test and I'm going to compare this test to it. At first, I'm just going to say this is just some other size alpha test. The book lets this be level alpha and makes it be a little bit bigger. So that's okay. So we'll just say that it's size alpha, and that's all we really know about it. Later on in the book, we're going to say, let's imagine this is a UMP test. So when we're proving part B, that basically says the likelihood ratio test is the only gig in town for coming up with the right test statistic. If you happen to do it a different way, it really is just a likelihood ratio test in disguise. So there's only one test in town that does this, and that comes from the likelihood ratio test statistic. So that's the uniqueness condition. So if you were math majors or took some proof classes, we're going to assume this is some other UMT test, and then we're going to show that it is that test. They are the same. So basic construct. So here is the master equation. Inequality, I should say. And this is going to look like this. Delta x minus this other test, delta star x, fx given theta 1, minus kfx given theta naught. This last part's in braces, so those are just multiplied into each other. And so they just say this real quickly in this book. They say this is true. And then you stare at this and you think, why is it true? I have no idea. But again, this is just an enumeration of cases. There's only 4 cases here. So all the cases are when this is a 1 or a 0 and when that's a 1 or a 0. So these are just indicator functions. And we checked that last time when we showed that this is positive. When this is a 1 and this is a 1, or this is a 0 and this is a 0, that's identically 0. When this is a 1 and that's a 0, this thing is positive. So that's this condition right here. So we're using that. When this thing is a 0 and that's a 1, this is negative and that's negative. So this is positive. So there's just 4 things you need to check. So that's true. And once you know that, everything is a lot simpler in this proof. So what they do next is they integrate over both sides. Integrating over the left-hand side is about the easiest thing you can do. It's still 0. Anything you do to 0 is still 0 unless you flip it over, which you're not allowed to do. So anything you do with 0 is still 0 if you're playing with it legally. Okay, so what we're going to do is we're going to integrate over this thing delta x minus delta star x f of x given theta 1 minus k f of x given theta naught dx. So I'm integrating over all of x. In all of this, that's what this means. So this is a definite. I'm just integrating over that whole entire space. Very typically, I don't write this stuff down. If I don't write it, I mean I've integrated over the whole space. So that's pretty typical. This can be re-expressed as 4 different power functions. So let me just show you what the power functions look like. Happens when I expand this out and I have the deltas next to the f's. I've got 4 different possibilities for the deltas next to the different f's. I've got f's with theta 1, f's with theta naught in there, and I've got 2 different delta functions. So each one of those integrals we can recognize. But just in general, this right here, I'll make this theta I dx. I can rethink about this as the expectation of delta x. This is under whatever this model is, x given theta I, if you like. So I can write that down. This is the expectation of an indicator, which is a probability function of its event. So what is the event? It's being in the rejection region. That's when it's a 1. So this is the probability that x is in the rejection region, given whatever this theta I value was. So, and this is the power function. That's the power. So I can rewrite this as 4 different power functions. Let's just put this aside. There's 4 of these that we're going to compute. We're going to rewrite this down like this. This is going to be b. We'll do the theta 1s first, so I'll just expand this one out into that, and then I'll expand this one out into that. Notice that there's a subtraction in between those 2 things. So this is going to be b theta 1 minus b star theta 1. So the b star, that's the notation they use in the book, that's the power function pertaining to that test. So the notation corresponds. So minus k B theta 0 minus B star theta 0. I'll let you stare at that for a while. This is that in disguise. When I expand the integral, break it up into 4 different terms, because there's just this additive thing. It's subtraction, it's the same thing. So I can break apart that integral into 4 different integrals and re-express those 4 different integrals as 4 different power functions. And it looks like this. Any questions about that? I think that's straightforward. So again, the hard part is this, and the hard part is recognizing this as these power functions. But once you do that, then basically the whole proof is standing right in front of you. You just have to understand what this stuff means based off of all of our conditions. So I'm going to replace that and cut that out here so we can stare at it. Any questions? Cool. You guys could do this proof if I asked you to do it next week on final, right? And at least you know what Neyman-Pearson says and you know what it doesn't say. So that's what I think is the ticket to ride to be able to do a hypothesis test these days. I think you need to be able to do Neyman-Pearson. If you ever see a p-value being computed, you should ask them, let me see the Neyman-Pearson test. Like the proof to the Neyman-Pearson lemma. And if they can't do it, walk away. Okay, maybe not. But I think we probably should understand what the guarantees are and when this stuff works well. I think that's half of what we see going on in science is people are just using these tools and saying somebody else came up with it. I don't know, I'm just doing it because other people told me to. This is what they told me in my class. And they're not wrong. So it's true. In Stat 101 class, we messed everybody up, I think. Am I wrong? We told people to just do it. So that's what I think Michael agrees with me. Yeah, they told them to just do it. So I don't know what can go wrong when people just tell people to do the wrong thing. Just do it, don't worry about it. So lots of wrong. So this is the black eye in statistics. I will say it's this thing in the sharp case. This is why computer science is winning, is they don't even touch this, you know? So they won't even play around with this. Let's just rewrite this equation. So B1, B theta 1 minus B star theta 1 minus K, that's just a positive constant. Let's just keep that in mind. I think I forgot to say that over here, but that's something positive. B theta 0 minus B theta 0 star. So we've got this inequality. Okay, let's just do the first part right here. We know what that is. Somebody help me out. It's alpha. This is the one that the book might have done a little bit differently. They might have said level alpha right here, and this is where they use this. I'm going to say, because I said it's size alpha, it's minus alpha. Okay, but the book, just so we can see this one little part and notice that it's really not that big of a deal, and for 9 o'clock in the morning, it really is not the whole point. If I had made this bigger than alpha, so, or bigger, so that's the level thing, then I would notice that this is negative right here. So if this was bigger right here, and then I would end up having this negative right here, and I could put this other bound on this and bound this equation and just do this. So that's what the book likes to do, is just say, hey, this thing could have been bigger, so I can put this bound on it. What I'm saying is it's 0. So I'm going to say it's actually equal, just to make it easier. Nothing crazy. So again, it's just this trade-off in power in the type 1 error. I could have made the type 1 error bigger, and it would just increase the power function. So let's just do size. If you're extremely concerned about the lemma thing, I'll let you untangle that a little bit more. So again, it's not that big of a deal. It's just this trade-off that always exists. If you push one thing down, the other thing goes up. So we're left with that right here. I still have this inequality. So this says B theta is bounded by, so B star theta 1 is bounded by that. And that's what that says. So boom, this is UMP. So that's our UMP test. So what we just showed is this is UMP. So that's it. It's bigger. So cool. It's not that hard of a proof. So once you at least get to this equation right here. So done. Let's go the other way. So we just did this. Okay, so part 2. This is just uniqueness. I used to always think when I was a math major, who cares? If there's 2 things that do something, that's great. If there's one thing that does it too, and I know how to do it, I can operate exactly the same. But I can understand why a mathematician might want to know if it's the only thing going. But I think in terms of engineering, it doesn't really matter. There's something that does something, nothing else out there exists, but I've got the right tool in hand, who cares? You know? So, but this would probably be half of your math major stuff. If you omitted all the uniqueness proofs, you wouldn't pass. So you have to find another major. Again, the whole point is that we found a test that's UMP, follow that procedure, that's good. If anybody ever comes up to you and says, I have another way of doing it, you can say it's just equivalent to the way I did it. Why do you know that? Because of part B. So we're going to assume delta star x is UMP. So what we're going to show is that this test is identical to delta x. That's what we'll try to prove. So assume delta star x is UMP and size alpha. So all the tests are size alpha. We already know delta x is UMP size alpha. How do we know that? We just proved it. So that was everything we did for part A, so we're already there. So let's just go back to this equation and see what it says. Let's get rid of this stuff. Stare at this thing one more time. So back to this exact same equation right here. What we just said is they're both UMP, so we know something about this right here. So it's 0. Both tests are UMP. So we look at the alternative space, that's this. We know that they have the same properties in that space, so they take on the same 1, 0 indicators at the same time because they're UMP, they're both UMP, so that thing is equal to 0. Now you could argue something about this stuff right here. Both tests are size alpha. So that's also 0 for the exact same reason. So in the case where delta star is also UMP, this is exactly equal to 0. This is equality. So this whole thing is actually equal to 0 over here. So that's what we just showed, is it takes on the equality value. So I have alpha minus alpha, that's 0. And I've got 2 UMP tests, so they must be taking on the exact same power. Exactly what is that number? I don't know what it is. I just know that the difference between them is 0. So that's 0. So then we're going to go back to our master equation. Let me just write this down again. Delta x, we'll do it in the integral form. Delta star x f of x given theta 1 minus k f of x given theta 0 dx. So we're integrating over this thing. So we know that the integral is equal to 0. This stuff isn't 0, so not 0. But this stuff must be 0. So there must be something in this equation, in the integrand, making this all 0. So what is 0? It's the leading part. It's the difference between these two tests. So this is equal to 0. So must be. Now you might say, I've had a measure theory class in there, so it's only 0 on all intervals of x. So it could be different on a point, because if I integrate over a point, that has 0 contribution to the integral. So I could make these different on points, but never on a set or an interval, and it wouldn't lead to anything differently. I do not believe in continuums in reality, so that doesn't actually happen. But if you wanted to be really technical and nuanced in everything, and mathematical and adhere to all the rules, we need to make this statement that this is 0 on all measurable sets. So anything that you're willing to measure. So what does it mean for a set to be measurable? It means you can take a ruler to it and measure it. It's not a point. That's what it means. If you really want a real definition, it has to do with an inverse mapping to everything. So, but I'm going to say you can make a measure. You can design a ruler to measure something. So that's it. So what we just said right here, based off of this stuff, is delta x is equal to delta star. Some people ask me why I sometimes write triple equal. I don't know. So if you want to do it like that, it doesn't mean anything great. It's just supposed to create emphasis. So they're the same on all measurable sets, anywhere that it's going to lead to any contribution to this statement that I made. So boom, check. So it's unique as well. That's pretty cool. I can imagine if I were Neyman-Pearson and I figured all this out, I'd be pretty excited to want to publish it and go to my newfound friend Fisher and show him, look what I did. It means that the p-value itself is not the important thing. It's alpha, and we're buddies, right? And it just didn't work out that way. So for some reason, they had to tangle for the rest of their careers. And I gotta admit, poor Neyman. So he's just hanging out. He's just a mathematician. So doing stuff, helping Egon with some math, figuring out what this all means, helping him concoct his proofs. So if you're not good at proofs, go find a friend that is good at proofs and team up with them, and that'll make you powerful allies. So he goes and finds Neyman. Neyman helps construct all of this stuff, and they run off and they show Fisher, and Fisher doesn't appreciate any of it. And honestly, Pearson couldn't understand why. So he didn't really understand the whole dilemma there. But it was a personal thing. I think that's infiltrated all of our field. Anyway, that's what it is. So that's Neyman-Pearson. We'll talk about on Monday p-values, exactly what the definition is. It's the probability of your data and more extreme data given the null hypothesis. They define that in a one-sided case in the book, so we'll talk a little bit about that. We'll prove that under the null, a p-value is uniformly distributed. So it's just a uniform random draw. So if you're thinking about under the null hypothesis, you compute a p-value. What you've really done is you've checked in your computing and you're checking to see if p ducks alpha. If I have a uniform random number and I want to see what's the probability of it ducking alpha, I know what the answer is. So what's the probability of a uniform 0, 1 ducking 0.7? It's what? 0.7, I think you said 0.6. So it's 0.7. So it's just that number. And that's why that's going on. So that's the error control in the type 1 in the null space. So p ducking alpha, it's got a type 1 error of alpha. That's because a p-value under the null hypothesis is uniformly distributed. That proof is in the book. Go ahead and look at that. We'll cover that. And then what I want to talk about just very briefly is also the sharp test. We'll see how brief I can be, but I'll try. I'll be forced to be brief. Here's what they do, just as a heads up. So this is just a precursor to what we'll see. Here's what they've done in the sharp test, is what they do for the one-sided test is they end up drawing some power curves. So for some one-sided test, let's just say X is normally distributed, mu naught, sigma squared, we'll assume sigma squared is known. If sigma squared is not known, replace it with S squared. So that's the typical thing. If you're a Bayesian or a non-Bayesian, they would do exactly the same thing. And so when I can come up with these power curves, so when I can calibrate this at whatever my value is, this is mu, and I'll be testing mu is equal to mu naught. So I look over here, mu naught, and I'd end up picking out whatever that power is right here. Call that alpha. That's my alpha level. And what they tell you in the book is for testing this test is biased. So because this is lower than right here over on this side. Over here, on this right-hand side, it's not biased over on this side, but because the power is going lower than right here, this point, this test is biased. So there is no unbiased test for the sharp test pertaining to the likelihood ratio test. So what they do is they say, well, let's just do this very unmathematical thing. So it's not an elegant theorem, as they say, let's just do another one of these power curves. This is supposed to be a reflection around this point. So, and now I have two different power curves. And what are they going to do? This huge mathematical thing. Erase that. And just get rid of it. And this is what they're going to do to force yourself to be in an unbiased situation. So now the power is higher everywhere than it is on the null space right here. So that creates an unbiased test. What are the ramifications? I guess if you're a scientist with lots of data, nothing bad. So everything is significant to you. So, and that's what ends up happening. So let me just say another case. If you're in this paradigm and you're computing p-values and you just want your p-value to duck alpha, it's very easy to do. And the prescription is go get more data. You'll eventually do it. We can think about that a couple different ways. We can either think we're drawing uniform random numbers. How many times do I need to draw a uniform random number before it ducks 0.05? You might be thinking if there's independence in everything, then it's just 20 times. There's not independence here because usually you would use your old data set as well. So you wouldn't go out and get a new data set that's double the size or something like that. You'd use your old data set. So there's a little bit of a relationship between the sequential p-values you want to go out and collect. But if you imagine you went out and collected all new data sets and your rule was, I'm going to go do the experiment again, but I'm going to double my data set. And I'm just going to keep doing that over and over again. You don't even need to double your data set, you just need to go get new data. So eventually, a uniform will duck alpha. And so that's great. You could have this procedure for rejecting anything out there in the world. And I think that some fields have caught on to this. It's too easy to collect data. And so in the big data world, or a world where we can all communicate pretty effectively, or at least quickly, maybe not effectively, but quickly, then we can get huge data sets like that. And so guess what happens to all those p-values for sharp testing? They all duck alpha. So again, I think the question is, if you're going to do that, you need to have a pre-specified distance from the null hypothesis. And what you would do with that is you would end up saying what power you wanted. So I want the type 1 error rate maybe to be 0.05 because I'm not a Babylonian. I looked up, they counted base 60. It's just totally nuts. So I have 5 fingers, they had 60 fingers, I guess. It was an astro thing. So they were looking at like calendars and that was meaningful to them.
We have it on our clocks.
Yeah.
Oh, hey, that is why that's
Yeah, because they also had 12 in their system. It wasn't just 60,
Yeah.
I think.
I see, so they could divide by 5. Okay, you guys know way more about this than I do. I need to go read Wikipedia. So I just hit the feeling lucky thing. It just gave me a number. Okay, yeah, okay, cool, clocks. So anyway, maybe you pick the type 1 error rate to be 0.05. So you can calibrate what alpha is with that. So, or pick your alpha level so that everything is 0.05. In the normal example, that would either be 1.645 if you were doing a one-sided test or 1.95 if you were doing a two-sided test. And then what you can do is you can say, I want my type 2 error rate to be, I don't know, 0.1 or something like that. So you don't want to go collect too much data. So you pick some other, multiple of 0.05, just for fairly arbitrary reasons. We have 5 fingers, we're not Babylonians. And then what you can do is you can calibrate what n is in that test statistic. And you can solve for both alpha and n. So now you have 2 equations and 2 unknowns. That gives you a stopping rule for what n you're supposed to go and collect. I think that's science. So if you have a reason for stopping, you've got some mathematical control on everything. So you say, I want to go collect this much data, and I would have had a type 1 error rate of alpha 0.05, maybe that's your alpha level, and your type 2 error rate is 0.1. Or you could drive that thing down and say, I want more ability to detect, and take the type 2 error rate and drive it down to 0.01 or something like that. You have to go collect more data. So, and then you can solve for n, then you go out there and you collect data. So if you're just sitting there collecting data until you see what you want, it will happen for you. And I think we see that game played all the time. So how abused can this be? Very abused. So, but what's the problem? People are getting money to do experiments. Everybody's running around. They've got good, significant things, so they feel good about themselves. They're able to publish stuff. And then the other side doesn't understand what we're doing. We have all of these false positives everywhere because of that. And so the reproducibility crisis emerges. So that's the big data era. So it used to be the case that coming by data was very, very hard to do. So you have to set up an experiment and tell people you only need to go collect 42 data points to have all these properties in this setup. So just go collect 42. But nowadays, we use this stuff in the sharp case where we just are able to accumulate as much data as we want in an observational setting. And I think that that's just total nonsense. So anyway, it does give you a method for always getting an answer you want. But again, I would argue that's probably not what scientists are supposed to be doing. So probably their utility functions are a little different than the utility functions that I'm thinking about. So be careful. So at the same time, you don't want to run around as a statistician and be the statistical police. So you want to explain things to people. So a lot of times what I do is I do an analysis the way I want to do it. And a lot of times I estimate and I don't do hypothesis testing. So there are cases where I'll do model selection, which is really akin to hypothesis testing. It has the same properties. I would say it enjoys the same properties, but it also suffers as well. So I know that when I do a sort of parsimonious model selection, I'm just in the ballpark of doing something reasonable. And I don't say that I have the truth, I just have a reasonable model. And then I try to enumerate other reasonable models for people. And I say this one is reasonable too. Look at all these reasonable models I can get. And then I say things like, look at the overlap in these models. So these are where these models all agree with each other. And that's interesting. That gives us a direction for doing a follow-up study. So what's the trade-off? Time. But I also recognize I don't get any more or less time in my life no matter what I do. Well, maybe that's not true. But we can at least imagine that we have some fixed amount of time, so we might as well do the right stuff. I'm going to say lots of stuff like that next week. So we'll go a little bit light. Any questions about all of this, or maybe what your misconceptions might be from other classes, or maybe where we're going in future advanced inference classes? I don't know. Some of you might just tap out right now. This is it. I liked it a lot better in Stat 101. I could just do whatever I wanted to do. I didn't have to understand it. Same.
What about more than two hypotheses, multiple hypothesis situations? Did Neyman and Pearson explore that themselves, or?
Well, you could think of the the simple versus the interval. So that's a lot of competing hypotheses. But what you do is you compare one hypothesis to the whole collection of other things. And then you've got a whole bunch of tests that you need to do. And there needs to be a multiplicity correction on all of that. And so that's where the Shefay stuff or the Bonferroni stuff comes from, is that you have all these competing hypotheses, and you need to come up with your effective alpha level for comparing all of those hypotheses. So if I'm rejecting a whole bunch of stuff with type 1 error rate of 0.05 and I've done it 17 times, what's my total error rate on everything? So what they try to do is come up with a bound on a total error rate that you should follow. So, but basically you do each hypothesis one at a time. Compare it to everything else, and then you can combine all of that and put a bound on it. I don't think that's great, I think it's okay. So in a Bayesian setting, you can compare all the hypotheses to each other simultaneously.
Yeah, it makes a lot more sense to me with the Bayesian.
Thank you.
So,
So I agree, I didn't come up with any of that stuff either, but yeah, I think so too. So the Bayesian, and I'll show you this as well, the Bayesian entertains all of their alternative hypotheses, no matter how you enumerate them. Sam's probably thinking of a question I asked in my Bayes class that shows you the differences in p-values and posterior probabilities on multiple hypotheses. I actually think the p-value thing is the winner in that example, but it's just for artifactual reasons we've used the wrong model. So I have you contaminate the model and see what happens. So that's something to keep in mind with all of this stuff, is that we're presupposing F. That's up on the board. It comes from F, and we get to know that. So there's these other follow-up questions of what happens if F is wrong. And I assure you F is wrong. You know, it's always wrong. And so what's the trade-off there when you have a partially misspecified F, which is always the case. And I think the Bayesian wins there as well, just because there's this balancing act between the errors you make. The errors you make in the alternative space and in the null space are exactly the same, so they hopefully balance each other in some reasonable way. Where in the sharp test, you don't use the alternative for anything. You're just conditioning on the null and computing everything. So you never balance it out with the alternative. Anyway, I'll say more about that on probably Wednesday. So if you want to know more about that, take another inference class. What else? I guess we're over. I thought we were over. Sorry, you guys. So one more time we'll go over. We'll probably do it at least one more. Thanks, you guys. And thanks for turning in all your homeworks and all of your hard work. I know that it's been pretty intense. You do have a few more practice problems to work through, and they'll help you on the line, but it shouldn't be excruciating. We'll do one more yes.